Hi everyone, welcome to my channel. This is my very first video, and I'm excited to explore some fascinating tech topics with you. We'll talk about cutting-edge technologies, quantum computing, encryption, and much more. In today's video, we're diving into the intriguing world of Bitcoin, how it's encrypted, why it's considered highly secure, and the big question: could quantum computers eventually break Bitcoin's encryption? Could the future of cryptocurrency be at risk? Let's dive in and find out. Bitcoin transactions are grouped into units called blocks. Each block contains a unique cryptographic hash, a digital fingerprint, that represents all the data within it, including transaction details. Crucially, every block also contains the hash of the previous block, creating a secure chain of blocks known as the blockchain. If anyone tries to alter a transaction in block 1, its hash immediately changes, breaking the link to the next block. This makes the entire chain invalid. Because changing one block means having to alter every subsequent block, tampering is nearly impossible, ensuring Bitcoin remains trustworthy and secure. If you're interested in exploring this topic further, there are plenty of excellent videos available online that explain the concept in greater detail. Bitcoin uses hashing to secure each block, but hashing only ensures data integrity in the chain. Eventually, to make Bitcoin useful, we need users. The unique and legitimate identifier of each user in Bitcoin blockchain is guaranteed by elliptic curve cryptography, often called ECC. ECC relies on the discrete logarithm problem, a math challenge so tough it keeps every transaction nearly impossible to crack. Let's examine the core math behind ECC, which relies on the elliptic curve discrete logarithm problem. This problem is defined as, given an elliptic curve, a point g, and another point q that is a multiple of g, namely q equals xg for some integer x. In the context of cryptography, q is the public key, x is the private key, and g is public generator point on the elliptic curve. It is computationally hard to determine the integer x because no efficient method exists to reverse the process, and this difficulty is what secures ECC. So, how challenging is it? In standard elliptic curve cryptography, the key length is 256 bits, meaning there are about 2 to the power of 256 possible combinations for the private key x. Using the most efficient classical algorithms available today, we need to perform roughly 2 to the power of 128 operations to find the correct x. If a supercomputer could perform 1 quintillion operations per second, it would still need roughly 10 to the power of 25 years to find the correct x, a duration that far exceeds the universe's estimated age of 10 to the power of 10 years. This immense computational challenge is what makes ECC extremely secure. ECC seems unbreakable with classical computers, but what if we add quantum power? In theory, a fully operational quantum computer could crack 256-bit ECC in just a few hours, turning today's secure encryption into tomorrow's solvable puzzle. So, how can a quantum computer crack ECC so fast? The answer lies in Shor's algorithm. Developed by mathematician Peter Shor, it uses quantum parallelism to factor large numbers and solve discrete logarithms, tasks that stump even the most powerful classical supercomputers. Here's a closer look at Shor's algorithm in action. Originally created for integer factorization, it relies on a quantum order-finding subroutine. By rapidly detecting patterns in large numbers, this method can also crack discrete logarithms, making today's encryption schemes vulnerable to quantum attacks. Let's zoom in on the quantum circuit behind Shor's algorithm. First, we prepare a superposition of k qubits in state 0 in the first register and L qubits in state 1 in the second register. Then we apply the Hadamard gate to all the k qubits in the first register, using the state after Hadamard gate to perform a controlled operation performs modular exponentiation on the second register. Finally, an inverse quantum Fourier transform in the first register reveals the periodicity hidden in those exponents. By measuring the state in the first register, we can factor large numbers or solve discrete logarithms, undermining today's encryption. At the heart of Shor's algorithm is the order-finding step. Let's illustrate why. In a typical integer factorization problem, we let n be the product of two large primes, p sub 1 and p sub 2. We pick a number g so that g is greater than 1 and smaller than n, and the greatest common divisor of g and n is 1. The goal is to find the order x, which is the smallest integer that makes g to the power of x equals to 1 modulo n. The quantum order finding algorithm can find the solution x very efficiently. Once the quantum circuit reveals x, we compute the greatest common divisor of g to the power of x divided by 2 minus 1 and n, and the greatest common divisor of g to the power of x divided by 2 plus 1 and n. These values reveal the prime factors p sub 1 and p sub 2. This is the core of Shor's algorithm, using quantum power to factor n efficiently. From the whole process, we can see that the most crucial step is to solve the order finding problem, g to the power of x equals to 1 modulo n. Note that at the heart of the discrete logarithm problem, both a composite modulus n, just as n in Shor's algorithm, and a prime modulus p can be used. In our following example, we will use a prime number p for simplicity. For discrete logarithm problems like g to the power of x equals 1 modulo p, a two-register quantum circuit can be used to solve such discrete logarithm problem where there is only one unknown exponent x. However, the elliptic curve discrete logarithm problem in ECC is q equals xg, which cannot be solved by a two-register quantum circuit, but that doesn't mean they cannot be tackled by quantum computers. For elliptic curve discrete logarithm problem q equals xg, it has its multiplicative analog g to the power of x congruent to y, modulo p. Such a problem can then be converted into a two-dimensional discrete logarithm problem with two unknown exponents, labeled a and b. For this 2D problem, a three-register quantum circuit can solve it. The top register handles exponent a, the second register handles exponent b, and the bottom register performs the controlled modular exponentiations. By combining quantum operations and the inverse quantum Fourier transform across both exponent registers, this circuit can reveal a and b simultaneously, solving the two-dimensional discrete log problem. In other words, the two-register circuit alone cannot break more advanced elliptic curve encryption, but the three-register circuit extends Shor's algorithm to handle two unknowns at once, making it a powerful tool against general ECC. Although the two-dimensional discrete log problem is more general in ECC, here we will use the simpler one-dimensional problem g to the power of r equals 1 modulo p as our main example to illustrate how the quantum order finding algorithm works. In this single exponent scenario, we will explain how to use a two-register quantum circuit to find the correct order r. By understanding the basics in this example, we can then apply the same principles to more complex discrete logarithm problems. First, we define operator u in the circuit. The operator u acts on the state labeled ket y, where y is state 0 or state 1. Then it produces the state labeled ket of g times y mod p. The eigenstates of this operator are written as ket u sub s, and each one has an eigenvalue of e to the power of 2i pi times s divided by r. It is not difficult to show two important properties of the eigenstate u sub s. First, each ket u sub s can be expressed as a superposition of the original basis states, reflecting the cyclical nature of the group. Second, all of these ket u sub states together form a complete basis, meaning any state in this space can be written as a combination of them. These properties are very important for the quantum order finding algorithm. Now, let's dive deeper into the quantum circuit, which can solve a one-dimensional discrete logarithm problem. We start by defining capital L in the second register as the ceiling of the base 2 logarithm of the prime number p, which tells us how many qubits we need in this register. We then define capital K to control the failure probability, epsilon. The smaller the epsilon is, the more qubits we need in the first register. Clearly, we can see the number of qubits needed in the first register K is related to the number of qubits L in the second register. Next, we look at the controlled U operation. If a qubit in the first register is 0, nothing happens to the qubits in the second register. But if it is 1, we apply the operator U to the qubits in the second register. By the definition of operator U, we will get state G modulo P state. Due to the Hadamard gate applied to K initial states 0, the second register U is raised to the power J, where J goes from 0 up to 2 raised to the power K minus 1. With different power J, after the controlled U to the power of J gate, the state 1 will evolve into state G to the power of J modulo P. So by carefully tuning L, K, and epsilon, we can make this quantum order-finding circuit highly accurate for solving the 1D discrete logarithm problem. Now let's see a concrete example. We want to solve 4 to the power of r equals 1, modulo 17. Because 17 is a prime number, we can use our earlier formulas to determine how many qubits we need in the first and second register. First, we set capital L to the ceiling of the base 2 logarithm of 17, which comes out to 5. These 5 qubits go in the second register. Next, we pick a failure probability of 0.25, which leads us to define capital K as 13. This means the first register will have 13 qubits in state 0. The circuit shown here uses the controlled U operation we just defined, with each qubit in the first register deciding whether to apply the operator U on the second qubits. By running this algorithm and measuring the first register, we can find the integer r, which satisfies 4 to the power r equals 1, modulo 17. So how this is done exactly? We divide our quantum circuit into 4 intermediate stages, and we will show how the combined quantum state is evolving at each stage. First, we initialize all the 13 qubits in the first register into state 0 and all the 5 qubits in the second register into state 1. This initial setup is our psi1 state. Then we apply Hadamard gates to every qubit in the first register. Then we get state psi2. Because each qubit evolves from ket 0 to an equal superposition of ket 0 plus ket 1, the entire states in the first register become a uniform superposition of all possible bit strings from state 0 to state 2 to the power of 13 minus 1. Meanwhile, the qubits in the second register remain in state 1 as no quantum gate has been applied yet. Then, for our next step, we apply the controlled U operations to the state in the second register. Each qubit in the first register now decides whether to apply U on the second register. If a qubit is in state 0, nothing happens to the second register. If it is in state 1, we apply the operator U to the qubits in the second register. Since the first register is in a superposition of zeros and ones, the controlled U operations to the second register also become a superposition state. After we apply the controlled U operations, the combined system moves into what we call psi3. The state psi3 is a sum over all j values from 0 up to 2 to the power of 13 minus 1. For each j, the first register is in the state ket j, and the second register is in the state that encodes 4 to the power j, modulo 17. Because 4 raised to different j values can cycle through a repeating pattern modulo 17, you see the sequence 1, 4, 16, 13, then back to 1, 4, 16, 13, and so on. The equation shows each state ket j paired with the resulting second register state. Finally, we group the terms by the second register values, so all j values that produce state 1, 4, 16, or 13 are collected together. This grouping makes it clearer that the second register cycles through 4 distinct outcomes, reflecting the fact that 4 has order 4 under modulo 17. In short, psi3 captures every possible way the first register can direct the second register to through controlled U operation, all in a single superposition. Although we can see repeated patterns in the second register directly in this mathematical expression, and from this pattern, it is very straightforward to get the order we are looking for, which is 4, by the way. However, in practice, such expression is unknown. We can only reveal the order after the final step. Anyway, let's continue. We can rewrite the state psi3 in a slightly different form, grouping terms in a way that highlights the repeating patterns. This new expression shows each second register value, like 1, 4, 16, and 13, paired with all the j values that produce it. By organizing the superposition in this manner, we reveal a structure that will become crucial later when we apply further quantum operations. In other words, even though psi3 is still a sum over many j values, collecting terms by their second register outcomes lets us see the hidden periodicities more clearly. We will use this regrouped form in the upcoming steps to help extract the order and solve the discrete logarithm problem efficiently. Next, we apply the inverse quantum Fourier transform to state in the first register. As a result, we arrive at the state psi4. In this new state, labeled by a sum over s from 0 to 3, Each term places the first register in a state we call tilde phi sub s. Tilde phi sub s is a state formed by k qubits, while the second register is in the corresponding eigenstate u sub s. The factor of 1 over the square root of 4 ensures the state remains normalized. Essentially, this step converts the superposition in the first register into a form where measuring it will directly reveal the hidden periodicities, and therefore the order of our discrete logarithm problem. Finally, the measurement in the first register takes place after the inverse quantum Fourier transform. This measurement projects the superposition of state psi 4 into one of the four states tilde phi sub s tensor product u sub s. There are four possible outcomes in the first register. Tilde phi sub 0 equals 0, tilde phi sub 1 equals 1/4, tilde phi sub 2 equals 1/2, and tilde phi sub 3 equals 3/4. So which result is useful for us? Let's use the continued fraction algorithm to help us. The continued fraction algorithm processes the approximate measurement results to find the best rational approximation, thereby recovering the order R we are looking for. The fraction must be in simplest form with numerator and denominator coprime so that the approximation uniquely identifies the true period R. With this coprime requirement, let's examine our four measurement results. The first measured result, 0 over 4, provides no useful information about the order. The next two fractions, 1/4 and 1/2, don't work either. This is because both 1/4 and 1/2 fail the coprime requirement. However, the final measurement result is 3/4, whose numerator and denominator are coprime. Thus, we conclude the denominator 4 is exactly the order R we're searching for. So, the final solution to our discrete logarithm problem is R equals 4. From the previous scene, it might still be unclear how we can get only 4 different values of tilde phi sub s when we do measurement to the first register. Let's have a closer look. In order to make the mathematical explain as simple as possible, we use one trick here. In quantum computing, there is a principle that says any qubits not measured at the end of a circuit can still be treated as if they were measured, without affecting other measurement statistics. Applying this idea, we can imagine measuring the second register first, observing state 16. Then in the combined quantum state psi 3, the state in the first register collapses into the state v sub 3, which is a superposition of the form 1 over the square root of 2 to the power of 13 times states ket 2 plus ket 6 plus ket 10, and so on. We next apply the inverse quantum Fourier transform only to v sub 3 here instead of all v subs. The inverse quantum Fourier transform of v sub 3 results in a new superposition alpha sub k times ket k, where k running from 0 to 2 to the power of 13 minus 1. When we finally measure the first register, the probability distribution p of k equals the absolute value squared of alpha sub k. It turns out this distribution is non-zero only for 4 discrete values of k, and it's 0 everywhere else. That's why we only have 4 possible different values when we measure the first register. The 4 distinct peaks in our probability distribution clearly show the hidden periodicity of the function 4 to the power of a modulo 17. But remember, when performing this experiment on a real quantum computer, it is not possible to see such a distribution. One can only see what measurement results can provide, which are the 4 values here. In these 4 different values, each of these values corresponds to a fraction. These fractions are the tilde phi sub s we just mentioned. They are used to approximate the phase phi, which is equal to s divided by the order R we seek. Although tilde phi is strictly equal to phase phi in our example here, in a real quantum computer, such case is very rare, if not impossible. The approximation sign is used here to reflect the fact that tilde phi is from experimental results, and it can only approximate the value of phase phi. After we have the value of tilde phi, our next step is to show how we can use these fractions to accurately determine the value of the order R. Similar to before, we use the continued fraction algorithm to help us pick the correct fraction to estimate the order R from our measurements. The first measured fraction, 0 over 8,192, provides no useful information about the order. The next two fractions, 2,048 over 8,192, which equals 1/4, and 4096 over 8192, which equals 1/2, don't work either. This is because the numerators and denominators are not coprime there. But the final measurement, 6144 over 8192, or 3/4, does satisfy this crucial condition. Its numerator and denominator are coprime. Applying the continued fraction algorithm, 3/4 is identified as a valid convergent fraction. Thus, we conclude the denominator, 4, is exactly the order r we're searching for. So the final solution to our discrete logarithm problem is r equals 4, which is exactly the same value we obtained when measuring only the first register. As we've just seen from our example, Shor's quantum order finding algorithm can efficiently solve the one-dimensional discrete logarithm problem. To tackle larger primes, all we need to do is increase the number of k and l for qubit in register 1 and 2. But exactly how many qubits would a quantum computer need to crack a real-world Bitcoin encryption problem? Typically, the prime number p used in Bitcoin's elliptic curve cryptography has 256 bits, roughly the size of 10 to the power of 77. Plugging this into our formula from earlier, we find that the first register requires 515 qubits, and the second register requires 256 qubits. In total, a quantum computer would need only about 771 qubits to crack Bitcoin's encryption system. Wait a minute. Does that mean Bitcoin's encryption could realistically be cracked within the next few years, given that we only need around 771 qubits? Fortunately, the answer is no. The catch is quantum error correction. Real-world quantum computers face significant errors and noise. To correct these errors, quantum computers need many additional qubits to detect and correct the errors. Currently, one of the best-known methods is the quantum surface code. For a reasonable error correction level, such as a surface code with a distance of 5, each logical qubit requires about 25 physical qubits. That means, to practically crack Bitcoin's encryption, we'd actually need around 19,000 physical qubits, still a very challenging target for today's quantum technology. But that's also not the whole story. If you still remember, the general elliptic curve cryptography problem is actually a two-dimensional discrete logarithm problem, requiring a quantum circuit with 3 registers instead of 2. In such a 3-register quantum circuit, the top register finds exponent A, the middle register finds exponent B, and the bottom register is for the auxiliary qubits. This means the number of qubits required is even larger. Specifically, we need 2 sets of k qubits for the 2 unknown exponents A and B, plus L qubits for the second register. For the Bitcoin example, that means 256 qubits for the second register, plus 515 qubits multiplied by 2 for the exponent registers, giving a total of 1,286 logical qubits. When taking into account the quantum error correction, just like we did before, the total number of physical qubits required jumps dramatically. With a quantum surface code at a distance of 5, this leads to around 32,150 physical qubits, far beyond current quantum computing capabilities. So, considering all we've discussed, breaking Bitcoin's encryption with a quantum computer is theoretically possible, but not as straightforward as it might first appear. Although Shor's algorithm clearly outlines how quantum computers could efficiently solve discrete logarithm problems, building an actual quantum computer powerful enough to threaten Bitcoin remains extremely challenging. Given the current pace of quantum technology development, along with the complexities of quantum error correction and scaling up physical qubits, experts generally estimate it'll take at least another 20 to 30 years before such a quantum machine could realistically exist. That doesn't mean quantum computing isn't useful in the meantime. Even as we work toward large-scale, fault-tolerant quantum devices, smaller quantum machines are already finding potential applications in optimization, simulating quantum systems, AI and machine learning, finance, drug discovery, and materials design, pushing the boundaries of what's possible in each field. Therefore, while quantum computing holds incredible promise and potential threats for encryption methods like Bitcoin, there's still plenty of time for researchers and developers to transition to quantum-resistant cryptographic techniques. For now, Bitcoin encryption remains secure, but the clock is ticking.